Now that we have a pretty good idea what energy actually is, we want to look at what happens when the energy of a system changes. Whenever we have a change in energy, we say that work has been done. So in our lab where we ran up the stairs, we did work because our gravitational potential energy changed. We had to do work to get to the top of the stairs. One thing to be aware of is that work can only occur when something has moved. Work involves both a force and a distance. Applying some force to move an object does work on the object. In equation form, we write that work is equal to the force being applied times the distance the object moves. The F in this equation represents force and is measured in newtons. D represents the distance the object moves and is measured in meters. When multiplied, the label becomes a Newton meter. In physics, this is shortened into a joule. So work is measured in joules, just like energy. This makes sense since we defined work as a change in energy to begin with. So just to be clear, two things must happen for work to be done. First, there must be some application of a force. And second, something must move. If you push against a stationary brick wall for several minutes, what can we say is happening? You are pushing on the wall, so you are most definitely applying a force. And Newton's third law says that the wall is pushing back on you with that same force. But are you doing any work? Since neither the wall nor you are moving, there is no work being done. So you do no work on the wall, and the wall does no work on you. Now, if you lift a barbell, you are applying a force and the barbell moves. Since the force causes the motion, we can say that work is being done. In this case, the change in energy is due to the barbell moving up, so the height changes. This means the change in energy is due to gravitational potential energy. Gravitational potential energy is found by taking the mass times the change in height times g. So if we double our mass, we will double the amount of gravitational potential energy. This in turn means we will do twice as much work. Let's say we take 2 loads of some mystery construction material and lift it 2 stories off the ground. Is it true that we would be doing twice as much work as if we were lifting only one load the same distance? It is. This is similar to our barbell example. Lifting twice as much mass will mean that twice as much work is being done. What about if we lift one load of construction material 1 story high? Is it true that we would be doing twice as much work if we lifted it to the 2nd story? Our change in energy is still gravitational potential energy with changes with height. So yes, if we lift the load twice as high, it will be doing twice as much work. Now what about this one? We have 3 10-Newton balls that are being lifted off the ground. One ball is lifted straight up, the second ball is rolled up an incline, and the third ball takes the stairs. Which one does more work? Since the weight of each ball and the height each ball is moved is identical in all 3 situations, all 3 balls do the same amount of work. It doesn't matter what happens in between, they are all 3 lifted to the same height, so the same amount of work is done on each one. So what if we have a 10-kilogram pumpkin and it is moved horizontally 5 meters at a constant velocity across a level floor using a horizontal force of 3 newtons? How much work is done in moving the pumpkin? We are given the mass of 10 kilograms, the distance that it moves as 5 meters, and the force used to push it as 3 newtons. It is important in these problems to determine what direction the motion is in, because that is the direction of the work. In this case, the pumpkin is moving in a horizontal direction, so the work will also be done in a horizontal direction. Remember that work is equal to the force times the distance. So from here, we just plug in the force that we use to push the pumpkin and the distance that it travels in that direction, and we end up with 15 Newton meters, or 15 joules of work being done on the pumpkin. What if we lift a 20 Newton pomegranate at a constant velocity from the floor to a height of 1.5 meters? How much work is done on the fruit? Now here we are given the weight of the pomegranate, which is the 20 newtons, and the distance that we lift it. Since the motion is in the vertical direction, we can say that the force being applied to it is the same as the force of gravity acting on it, since it's moving up at a constant velocity. So again, work is equal to the force times the distance. We take the weight, or the force of gravity, and multiply it by the distance we lift it to find out that we are doing 30 joules of work on our pomegranate.